In this video, I want to talk about Newton's second law of motion. Before I get into the details of Newton's second law, I need to talk a little bit about net force. Remember that Newton's first law states that inertia keeps an object from changing its motion unless an unbalanced force is present. And you know from preparing force diagrams, often several forces are acting upon an object at the same time. Now, force is a vector quantity, so it has both a magnitude and a direction, and it is possible that two forces of opposite direction can cancel each other out. So the result is that it's the net force we're concerned about, or the vector sum of all the forces, because that's what actually is creating the unbalanced force. Let's look at these examples below. In this first force diagram, we have the force of gravity of 800 newtons pulling this object in a downward direction. And the force of tension, must be hanging from something, of 1,200 newtons pulling that, giving a direction of the force in the upward direction. And so the 800 in a downward direction, if we kind of draw it in here, is going to cancel out part of that upward force. So the end result, or the vector sum, is a force of 400 newtons upward as the net force on this object. In the second object, gravity, again, is 800 newtons, but the air resistance force in this case is 600 newtons. And so the canceling out would happen in this direction, and so this little bit that's left over gives us 200 newtons in a downward direction as the net force on this object. In this final force diagram, we have gravity of 50 newtons and a normal force of 50 newtons. So those are going to just cancel each other out completely, leaving the frictional force of 20 newtons being the only force, or the net force, acting on this object. Let's look at some other problems. You can figure out the individual forces by thinking about what the net force is and sort of approach this problem from the other side. So in this first example, the net force is 0 newtons, which means every force acting on the object is going to be canceled out by another force with the opposite direction but the same magnitude. So we have 200 newtons in a downward direction. That means we're going to have 200 newtons in an upward direction. If we have 50 newtons going to the right, we're going to have 50 newtons going to the left. Our second object has a net force of 900 newtons up. So we have 200 newtons showing in a downward direction, which means we have to have 200 newtons in an upward direction to cancel that out, plus another 900 that ends up being the net force. So our total, if we add those two together, is that we have to have 1,100 newtons in an upward direction in order to create a net force of 900 newtons in an upward direction. Our third object has 60 newtons to the left. So again, in the upward and downward, they have to be canceling each other out. So we have 300 newtons up. That means we have 300 newtons down. If we're going to end up with 60 newtons to the left, and we're seeing 80 on the diagram, that means 20 of them have to be there to going to the right to cancel out, because 80 minus 20 will give us our 60 newtons to the left as our answer. And in our last diagram, we're just showing one force with a number that we've got 20 newtons going to the left showing on the diagram, but our net force is 30 newtons to the right. And so that means we've got 20 newtons that are going to cancel out and then add another 30 newtons to the right, giving us 50 newtons to the right. The up and down really doesn't matter on this. You can put any number in there you want. So we'll say, 100 down and 100 up, because they're just going to cancel out since the only force, or the net force, is going to be 30 newtons to the right. So now you've got a sense of net force. Let's look at Newton's second law. So Newton's first law is predicting the behavior of objects at equilibrium in balanced forces. But Newton's second law applies to objects experiencing acceleration due to the unbalanced force. Remember, a force is not needed to maintain a motion. Inertia is what's going to do that. But to change it or to cause acceleration, you need that unbalanced force. Acceleration itself is dependent on two factors: the net force acting on the object, so that's, strictly in newtons, how big is it? And then the mass of the object, because mass, of course, is directly connected to inertia. The more mass something has, the more inertia or the more resistance it has towards changing its motion. We can think of acceleration as a math equation, and we'll be working with this equation over the next couple slides. Acceleration is our net force divided by the mass, or more typically we see it written this way, that the net force equals mass times acceleration, or F equals ma. Remember that the unit for force is the newton, which is 1 kilogram times 1 meter per seconds squared, because we have both our mass unit here and our acceleration unit, which fits right into the Newton's second law equation. So since Newton's second law can be written as a math equation, we can rearrange that equation to find any of the three variables involved. Sort of the standard format where we're looking for the force would be multiplying mass times acceleration. But if we're looking for the mass, well, that would be acceleration divided by the net force. And of course, acceleration would be the force divided by the mass. So we have a table down below with various forces, masses, and accelerations, but some pieces are missing. So let's look at this first row. We have an object that is experiencing a net force of 10, and this object has a mass of 2. And so our equation tells us that we take our net force, which is 10, divided by the mass, which is 2, which gives us an acceleration of 5 meters per second squared, or per second per second. On the second problem, we have a net force of 20, but again, a mass of 2. And so this would be 20 divided by 2, or an acceleration of 10 meters per second, or per second squared. Our third problem, we've got a force of 20, but our mass has increased to 4. So here we would have 20 divided by 4, which gives us an acceleration of 5 meters per second squared. In our fourth row, we are missing the net force. So net force is just caused by mass times acceleration. So we've got a mass of 2, so it'd be 5 times 2, which gives us a net force of 10 newtons, because newtons are unit for force. And then our last one, we have our force of 10 and an unknown mass, an acceleration of 10. So in order to figure out mass, we take the acceleration and divide it by the net force. So 10 divided by 10 is going to give us a mass of 1 kilogram. So notice when a change is made in net force, the same change will occur in acceleration. This is a direct relationship. So in our first two rows, our net force is doubled and our acceleration is also doubled. If the force stays the same as in our second and third rows, but we are doubling our mass, so our mass is going from 2 to 4, you can see the acceleration is going from 10 to 5. And so this is showing that inverse relationship. The mass is doubled, but the acceleration is cut in half. The last point I want to make is that the direction of the net force is always going to tell you the direction of the acceleration. Remember that the direction of the acceleration is not necessarily the direction of the motion, but the direction of the net force always determines the direction of the acceleration. So the next topic I want to talk about is free fall and air resistance. Even though it seems counterintuitive, experimentation has shown that all objects, regardless of their mass, experience the same acceleration in free fall. When an object is in free fall, the only force acting on it, or its net force, is going to come from the force of gravity. And all objects accelerate at a rate of 9.8 meters per second, which we often, just for math purposes, round it off to 10 meters per second. We call this the acceleration of gravity. It gets its own letter. It's written in formulas as g. Objects that are in free fall where air is present will reach what is known as a terminal velocity, or an ending velocity, where acceleration will stop occurring. They will still have motion, but they will not be getting any faster. So how does Newton's second law help explain these two situations that we see, that all objects will fall at the same acceleration and that terminal velocity will be reached? Let's look and see. So as previously stated, in free fall, gravity is the only force acting on an object. Newton's second law tells us that the acceleration of an object can be calculated by the force on that object divided by the mass. And so we can think about this as every kilogram of mass experiences a force of 9.8 newtons during free fall acceleration. As you add more kilograms, that means more newtons of force are going to be present on the object in total, because every individual kilogram of mass is going to be experiencing this force of 9.8 newtons, or rounded off to 10. So a little illustration, we have an elephant and a mouse following here. Elephants have a big mass, and so they're going to have a corresponding big force, because every kilogram is going to have 9.8 newtons pulling on it. So the total force is going to be much larger than a mouse that has a small mass and doesn't even have 1 kilogram to have the 9.8 newtons pull on it. Free fall acceleration is a property of location, so that if we were having free fall happen in a location other than Earth, the objects would have different accelerations. And interestingly, since Earth is not a perfect sphere, and so certain sections of Earth are more massive than others, it sort of bulges around the equator, there's also a slight variation in the acceleration due to gravity on Earth, so that objects that are falling closer to the equator are going to have a slightly faster acceleration than 9.8 newtons than objects falling on the poles. When an object is falling through air, which is certainly what happens on Earth since we live in an atmosphere, then we have the force of air resistance. Air resistance is caused by the collision of the falling object with molecules of air, because air is not empty space, it has particles of a gas in it. As an object falls with greater speed, it collides with more air particles, and so you get greater air resistance. So as speed increases, air resistance, or friction with air particles, increases. And also, if an object has a high cross-sectional area, if there's a lot of it running into the air particles, then it's going to collide with more air particles and experience greater air resistance. That's why parachutes are so helpful. If you think of a little person falling through the air, their cross-sectional area is very, very small as compared to if they are in it with a parachute. There's going to be a much larger cross-sectional area. As an object falls, then it's going to pick up speed because of the acceleration of gravity, and also experience more air resistance because it's running into more air particles. If the air resistance equals, or the force that comes from the air resistance equals the force that is coming from gravity, then the object will stop accelerating. And this is what is known as terminal velocity. It is still moving, it still has velocity, but the acceleration has gone away. Less massive objects will experience terminal velocity sooner, and then overall they will fall more slowly than more massive objects. So if you think about, dropping a bowling ball and a feather, a bowling ball would take quite a bit longer to reach terminal velocity because it's much more massive, where then a feather is going to be very quickly reaching its terminal velocity and falling much more slowly to Earth. We can calculate this using Newton's second law to determine when an object is going to reach terminal velocity. So we have an 85 kilogram skydiver in 4 sort of given moments in time as it falls in free fall before he or she deploys the parachute. So in the beginning, sort of when the person has jumped out of the helicopter and is plummeting towards Earth, we have just the force of gravity working on this person, and so they have a force of gravity of 833 newtons. And so the acceleration is going to be the net force divided by the mass. So in this case, we have 833 divided by 85 kilograms, and that's going to give us an acceleration of 9.8 meters per second squared, just as you would expect if the only force acting on this object was gravity. It's our acceleration due to gravity. But now we have some air resistance coming into the picture after it the person has fallen for a short amount of time and has increased their speed due to this acceleration. And so now we have the air resistance giving us 350 newtons in an upward direction to cancel out some of our force of gravity. So if we do the math and figure out how much removing the upward direction resistance, we get a total Newton force of 483 newtons. And again, this is an 85 kilogram person. And so now their acceleration has decreased to 5.7 meters per second squared. The air resistance had slowed down the acceleration, even though their overall speed has increased because acceleration has been going on since the moment they jumped out of the helicopter. After some more acceleration has occurred, now we have air resistance of 700 newtons. And so now you have 133 newtons as a net force on this 85 kilogram skydiver. And so now our acceleration has decreased to 1.6 meters per second squared. So again, the speed is still changing, acceleration is still occurring, but it is much more slowly accelerating than when this person first jumped out of the helicopter. And then finally, when terminal velocity has been reached, the air resistance and the force of gravity is exactly the same. And so, of course, that would be net force would be 0 over this 85 kilogram. And so that gives us a 0 acceleration. Now, in real life, massive objects will take a long time to reach terminal velocity, and there may not be enough of a distance in the free fall situation that terminal velocity ever being reached. Of course, also realize terminal velocity does not mean something is slowed down or has stopped in the air. That just means no more acceleration is occurring. So check your understanding. Can you analyze a free body diagram to determine the net force acting on an object? Do you remember the basic equation for Newton's second law? Can you use this equation to explain how acceleration is directly related to the amount of force applied and inversely related to the mass of the object? Can you explain how the acceleration of gravity and air resistance affect an object in free fall? And can you do the simple calculations using Newton's second law to determine acceleration, mass, or net force acting on an object?